According to Straits Research, Secure Access Service Edge, or SASE, solutions are rapidly gaining traction. Their market is projected to skyrocket from $5.11 billion in 2025 to a staggering $25.96 billion by 2033. As organizations increasingly adopt these transformative cloud-native frameworks, they must be vigilant in navigating the evolving landscape of cybersecurity threats that specifically target these architectures. Hey everyone, thanks again for tuning in. If you like the content, do me a favor, click subscribe and hit the like button. Now back to the video. Cloud-native environments introduce unique security challenges for SASE implementation that extend beyond traditional network security concerns. As organizations increasingly adopt cloud-native architectures to support their SASE frameworks, they face an evolving set of vulnerabilities that threaten actors' active targets. Robust container security practices are a must in cloud-native SASE deployment. Attackers often exploit vulnerabilities in container-based images that have not been regularly updated with security patches. These vulnerabilities can be initial access points, compromising the entire SASE security stack. Therefore, organizations must prioritize rigorous container security practices, including regular image scanning and updates to mitigate these risks effectively. Misconfiguration remains one of the most prevalent cloud vulnerabilities that affect SASE environments. Security research shows configuration errors in IAM settings, firewalls, and network routes are among the top cloud-native threats. These misconfigurations can inadvertently expose management interfaces to unauthorized access, creating opportunities for attackers to compromise SASE infrastructure. The recent exploitation of pan-OS management interfaces in Palo Alto Networks demonstrates this risk, with attackers actively targeting critical vulnerabilities in firewall management systems. API security presents another critical challenge because insecure APIs can undermine SASE security controls. Cloud service providers expose management APIs that organizations use to provide and orchestrate their SASE resources. But these internet-accessible interfaces create an expanded attack surface. Without proper authentication, authorization, and data validation, these APIs are prime targets for exploitation, potentially allowing attackers to gain unauthorized access to SASE management planes. Multi-tenancy vulnerabilities pose unique risks in cloud-native SASE environments. Exploiting system and software vulnerabilities within a cloud service provider's infrastructure can lead to tenant separation failures. This can enable attackers to move laterally from one organization's resource to another, compromising the isolation on which SASE architectures depend for security. Limited visibility across dynamic cloud environments complicates security efforts. Cloud-native resources, rapid scaling, and changing nature make it challenging to maintain comprehensive security visibility. Without proper monitoring and telemetry tools for real-time threat detection, organizations may fail to identify attacks targeting their SASE infrastructure until significant damage occurs. To address these vulnerabilities, organizations implementing SASE must adopt cloud-native security strategies, which include the following: implementing robust identity and access management with strict privilege controls, encrypting sensitive data both in transit and at rest, conducting regular security assessments of cloud configurations, deploying continuous monitoring solutions designed for dynamic cloud environments, integrating security into development workflows to address the challenge that developers often lack security expertise. As SASE adoption accelerates alongside increased cloud adoption, addressing these cloud-native vulnerabilities has become increasingly critical for maintaining effective security postures. Organizations must balance the operational benefits of cloud-native SASE implementation with the security requirements to protect against these evolving threats. Zero Trust implementation challenges. Zero Trust Network Access, or ZTNA, is a cornerstone of effective SASE implementation, but organizations face numerous challenges when implementing this security model within their environments. Understanding these challenges is crucial for developing strategies to overcome them and maximize the security benefits of SASE deployment. Network complexity and interoperability issues represent some of the most significant barriers to zero trust implementation. Many organizations operate with hybrid infrastructures consisting of numerous servers, proxies, databases, internal applications, and SaaS solutions distributed across cloud and on-premises environments. This complexity is compounded when organizations attempt to secure systems composed of legacy and new hardware and applications, creating substantial obstacles to achieving comprehensive zero trust coverage. Resource constraints frequently impede zero trust adoption within the SASE frameworks. Implementing zero trust architecture requires significant financial investment, time, and skilled personnel. The initial setup involves substantial changes to the existing network infrastructure, continuous monitoring, and deployment of advanced security tools, all of which have already limited IT resources. Healthcare organizations and other large enterprises particularly struggle with the resource-intensive nature of zero trust implementation, including the need for specialized expertise, security tools, and infrastructure upgrades. Change management presents another critical challenge when transitioning to zero trust in SASE environments. Implementing a SASE solution with zero trust principles involves significant changes to traditional infrastructure that may have become entrenched in corporate working practices. Moving too quickly can compromise productivity and collaboration, potentially leaving security gaps until the new setup is fully operational. This disruption makes careful change management essential, with clear milestones and stakeholder communications throughout the implementation process. Cooperation between networking and security teams becomes problematic during zero trust implementation. Transitioning to SASE with zero trust should be a joint effort that accounts for network and security functions. However, security teams frequently control the deployment process, with network technicians factoring in as an afterthought. This siloed approach can lead to implementation gaps and operational inefficiencies that undermine the zero trust model's effectiveness. Comprehensive visibility is crucial in distributed environments to establish effective access policies. Without a clear view of network traffic, user behavior, and application access patterns, organizations struggle to detect anomalous activities that may indicate security threats. This visibility challenge is particularly acute in distributed environments where users access resources from various locations and devices. Organizations can address these challenges by adopting several strategic approaches. Start by thoroughly assessing the current environment to identify critical assets, access patterns, and potential security gaps. This proactive approach ensures that the zero trust model is implemented, tailored to the organization's specific needs and vulnerabilities, enhancing its effectiveness. Implement zero trust gradually, beginning with high-value assets and expanding incrementally. Ensure collaboration between networking and security teams from the planning stages. This united approach ensures that all aspects of the SASE deployment are aligned and working towards a common goal, enhancing the effectiveness of the zero trust model. Select SASE vendors with strong integration capabilities and comprehensive support. Document and map application usage before starting ZTNA implementation. Clean up application access to to establish a baseline for zero trust policies. Prepare for operational overhead and complexity with adequate staffing and training. By acknowledging these challenges and developing targeted strategies, organizations can implement zero trust principles within their SASE frameworks, creating more resilient security architectures that effectively protect distributed resources in today's dynamic threat landscape. SD-WAN integration risks. SD-WAN technology is a critical foundation for SASE implementations, but its integration introduces significant security vulnerabilities that make it vulnerable to exploitation. Understanding these risks is essential for organizations to deploy SASE frameworks in hypervisor secured environments. Direct internet access at branch locations creates substantial security exposure when the SD-WAN is improperly configured. Unlike traditional WAN architectures that route traffic through centralized security hubs, SD-WAN enables localized internet breakout points that can expose new attack surfaces without proper security controls. This architectural shift fundamentally changes the security perimeter, requiring organizations to implement comprehensive protection at every endpoint rather than relying on centralized security models. Management interface vulnerabilities represent a particularly dangerous threat vector in SD-WAN deployment. The remote orchestration capabilities that make SD-WAN attractive also create a single point of failure that, if compromised, provides attackers with network-wide access. This risk was demonstrated in 2023 when a critical vulnerability in Cisco SD-WAN vManaged software allowed unauthenticated attackers to retrieve sensitive information, potentially compromising entire networks. Similarly, another vulnerability in Cisco Catalyst SD-WAN Manager enabled authenticated attackers with read-only privileges to bypass authorization controls and roll back controller configurations that could be deployed to downstream routers. Configuration errors frequently undermine SD-WAN security, with misconfigurations ranking among the most common vulnerabilities. These errors include inadequate encryption implementation, improper network segmentation, and insecure API configurations that provide easy entry points for attackers. The complexity of SD-WAN deployments exacerbates this risk as organizations struggle to maintain consistent security policies across distributed environments. Authorization bypass vulnerabilities present another significant threat to SD-WAN security within the SASE frameworks. In multi-tenant environments, these vulnerabilities allow authenticated attackers to access information about other tenants, make unauthorized configuration changes, or potentially cause denial of service conditions by taking tenants offline. This cross-tenant access undermines the isolation principles that secure multi-tenant architectures depend on. Organizations should implement several key security strategies to mitigate SD-WAN integration risks. First, deploy a comprehensive SASE framework that integrates SD-WAN with cloud-based security functions to ensure traffic is secured at every endpoint while maintaining visibility across the network. Second, implement network segmentation to create isolated zones that contain potential security breaches, limiting lateral movement opportunities for attackers. Third, adopt a zero-trust security model with strict access controls, particularly for SD-WAN management interfaces, supplemented by multi-factor authentication and role-based access control. Fourth, regularly update SD-WAN software and security signatures and conduct thorough security testing to identify and remediate vulnerabilities before they can be exploited. Lastly, consider vendor-neutral branch networking platforms that can host or integrate with various SD-WAN and security service edge SSE solutions to create a more flexible and secure SASE architecture. The convergence of SD-WAN with security services through SASE represents the future of a secure network architecture. Still, this integration must be approached carefully to address these inherent risks. As one security expert notes, SD-WAN prevents the need for traffic to be routed via a centralized hub before accessing cloud resources, which creates efficiency and introduces new security challenges that must be addressed through comprehensive security planning. Kubernetes misconfigurations. Kubernetes environments within the SASE architectures present unique security challenges, with misconfigurations representing one of the most significant vulnerabilities. These configuration errors can create substantial security gaps that allow actors to actively exploit containerized workloads and gain unauthorized access to sensitive resources. Role-based access control, or RBAC, misconfigurations are among the most dangerous Kubernetes security issues. Overly permissive RBAC settings grant excessive permissions to users, service accounts, or groups instead of adhering to the principle of least privilege. For example, granting the cluster admin role to a default service account is particularly hazardous because this role has unrestricted access to all resources across the entire cluster. If a remote code execution vulnerability compromises a pod in the default namespace, attackers can impersonate the service account and perform any action on any resource within the cluster. Insecure workload configurations create additional attack vectors in a Kubernetes environment. Critical security issues include host namespace sharing, enabling host PID, host IPC, host users, and host network privileged container settings, and host path volume mounts. When containers run with these insecure configurations, they can access host resources, potentially compromising systems. For instance, mounting the host's root file system into a pod allows the container to access and modify any file on the host, creating an extreme security risk. The misconfigured cluster components represent another significant vulnerability category. KubeAPI server, the central management point for Kubernetes operations, is particularly vulnerable when improperly configured. Administrators may inadvertently allow anonymous access by leaving the anonymous auth flag set to true, which is its default setting, exposing API server endpoints without proper access controls. This misconfiguration enables attackers to query sensitive information regarding nodes and pods using simple commands. Network policy misconfigurations further undermine Kubernetes security in SASE environments. Common issues include incorrect selectors that fail to apply policies to intended pods, conflicting policies that interact unexpectedly, namespace limitations that do not account for cross-namespace communication, and missing default denying policies that implicitly allow unauthorized traffic. These network policy errors enable lateral movement within clusters once the attackers gain initial access. Authentication vulnerabilities present additional risks, particularly when the credentials are improperly managed. For example, developers may accidentally commit Kubernetes API credentials to public repositories, allowing attackers to retrieve and exploit these credentials to access cluster resources. This risk is magnified when credentials provide elevated privileges or when they are challenging to revoke once compromised. Policy enforcement misconfigurations across multiple Kubernetes clusters and cloud environments create governance challenges for security teams. Without centralized mechanisms for detecting, remediating, and preventing misconfigurations, clusters remain vulnerable to attacks. To mitigate these risks, organizations should implement robust security practices. Adhering to least privilege principles by granting only necessary permissions and using custom roles instead of cluster admin. Conducting regular audits of RBAC policies and network configurations to identify and remediate security gaps, implementing network policies that restrict pod communication and reduce the attack surface using namespace isolation with strict access controls to contain potential breaches. Deploying admission controllers and policy enforcement tools like Open Policy Agent Gatekeeper or Kyverno to ensure only secure compliant configurations are admitted to clusters. Regularly updating Kubernetes and container runtimes to address known vulnerabilities. As SASE architectures increasingly incorporate containerized workloads, addressing these Kubernetes misconfigurations is critical for maintaining a strong security posture. Organizations must implement comprehensive security governance to detect and remediate these issues before threat actors can exploit them. Emerging SASE threat vectors. Artificial intelligence and machine learning are revolutionizing the SASE landscape with enhanced threat detection capabilities. However, they simultaneously introduce new vulnerabilities. AI-powered systems can automate responses to detected threats, reduce mitigation time, and improve overall security posture. However, these technologies enable attackers to develop increasingly sophisticated attack methods targeting SASE infrastructures using tools such as Microsoft Copilot and OpenAI ChatGPT. The proliferation of IoT and edge devices presents another significant challenge to SASE security. These devices often lack built-in protection, making them particularly vulnerable to attacks. As IoT expands in scope and influence, SASE frameworks must evolve to provide unified security approaches that protect data across diverse devices while ensuring secure communication between edge devices and core networks. This challenge is compounded by the need to enforce zero trust policies for each device, requiring granular control to identify and mitigate risks early. Multi-tenancy vulnerabilities are emerging as a critical concern in SASE environments. SASE systems frequently employ cloud-based multi-tenant architectures in which different organizations share identical infrastructure. Without appropriate security mechanisms, there's a significant risk of data leaks or unauthorized access between tenants. Server-side attacks targeting the SASE hosting infrastructure, including exploitation attempts, software vulnerabilities, and misconfigurations, can lead to service disruptions through DOS attacks or more severe security breaches. Broken access control vulnerabilities represent an increasing threat to SASE implementations. These issues can manifest through overprivileged user profiles, where administrators lose sight of the user lifecycle. For example, when employees with administrative privileges leave a company while their login identity remains active, XSS and injection attacks provide additional entry points for malicious code, granting access to intruders through poorly calibrated access controls. Cloud-native container security challenges are becoming more prominent as SASE architectures increasingly rely on containerized environments. Security risks in these environments exist in three main areas: software vulnerability, shadow containers, and deployment problems. So according to the Verizon Data Breach Investigations Report, 14% of security breaches are linked to vulnerabilities as the initial access point. Similarly, approximately 13% of the issues can be traced back to misconfigurations in the software and infrastructure components that are configured. Kubernetes misconfigurations pose significant threats to SASE environments. The OASP Cloud Native Application Security Top 10 identifies insecure clouds, containers, or orchestration configurations as the primary risk. Common issues include publicly open cloud storage buckets, improper permissions on cloud resources, containers running as root, and containers sharing resources with hosts. These misconfigurations can expose workloads and clusters to severe risks, including unauthorized access, data breaches, and complete system compromise. Regulatory compliance challenges intensify as cybersecurity regulations, such as NIS2 and DORA, become more complex. While these regulations present opportunities to strengthen cybersecurity posture and secure additional resources, they also create implementation challenges for the SASE frameworks. Organizations must navigate these complex regulatory requirements while centralizing security policies to simplify compliance management. SASE implementations introduce latency concerns, particularly when traffic is routed through cloud-based security services or policy enforcement causes delays. This performance impact must be balanced against security requirements, particularly as organizations increasingly rely on real-time applications that demand minimal latency. The challenge is further complicated by the need to maintain comprehensive security controls without degrading user experience or application performance. As 5G networks continue to roll out, SASE frameworks must be adapted to integrate with this infrastructure while addressing new security challenges. The increased bandwidth and device density of 5G networks requires scalable security solutions that protect large volumes of traffic and connected devices. SASE implementations must implement dynamic security policies that adapt to the changing conditions of 5G networks to ensure consistent protection across all access points. Supply chain compromises represent an emerging threat vector because SASE involves various components and services that third-party vendors provide. Tampered software or hardware can introduce vulnerabilities that compromise the security stack. This risk is amplified by the trend towards single-vendor SASE solutions, which create potential single points of failure and vendor lock-in risks that could impact security resilience if the vendor systems are compromised.